Right. Thank you, Ian. Good morning, everyone. Today I'll be talking about modeling airborne transmission indoors using an advection-diffusion-reaction equation. And so our motivation is to study the risk of having an event indoor for a few hours. So say if we were holding this mini symposium actually in a physical location, what would be the risk of airborne transmission if someone in the room was infected? So airborne transmission, airborne disease are transmitted by the droplets produced by a person when they speak, cough, sneeze, or talk. And these droplets, as you heard from our speakers previously, can travel ballistically and fall to the ground within 2 meters or even more, as you heard from the first talk. Or the smaller droplets can float in the air and travel as a cloud for hours. And if you inhale these small droplets, then you may be infected. So we are interested in modeling these small airborne droplets, and these droplets are affected by many different physics. The first to consider is the diffusion of these droplets in the air, which occurs on this timescale of hours. These droplets may also be carried by the airflow in the room, leading to virus transport. Then these infected droplets may also be removed by the ventilation available in the room, whether that's natural ventilation through windows, open windows, or through air vents that are exchanging the air. Then we also have to consider the activity of the infectious person, the virus source. When someone coughs or sneezes, they produce a lot of droplets and in a turbulent jet. But if they're talking, they are producing a lot less droplets, but because one can talk or breathe for a very long time, the number of droplets that are produced can be very great as well. And then their behavior can also be affected by whether they are wearing a mask, and also what the viral load of the person is. So some people have been identified as super spreaders, and these people are shedding the virus at a much higher load than other people. Then these droplets will have a few different particle effects. The first is gravitational settling. The second is evaporation. The droplets are mostly made of water, and they evaporate quickly within about a minute to an equilibrium size. And we have virus deactivation. So if the virus in the droplets do not find a host within a certain amount of time, usually about 1 to 2 hours, the virus will start to deactivate. Finally, the virus receivers or the susceptible people's behavior may also affect the probability of airborne transmission. Whether if these people are, for instance, moving around a lot, they could be mixing the air in the room or causing a difference, a thermal gradient because of their body temperature. So to model all these different physics, we could use computational fluid dynamics. But as you've heard, that this could be a complicated problem, and even with a supercomputer, these simulations could take days. And if anything has to be changed, any parameters has to be changed, it could require the entire simulation to be rerun and would take all that time again. So on the other hand, many experts have been using a simplified model, which is the Wells-Riley model, which assumes the room is well mixed. So here is the governing equation for one of the extensions to the Wells-Riley model, where you can see that they've essentially taken the source strength and averaged it over the room volume. So they are assuming that the particles are transported instantaneously and ignoring the effects of the airflow and the diffusion on the. And then they model the ventilation, biological deactivation of the virus, and the gravitational settings as first order removal terms. And so the advantage of this model is that it's very easy to implement and the simulations are very fast. So, and this was quickly applied to the COVID-19 pandemic. So for instance, the first papers by Buonanno et al. Came out just a little bit after Italy was struck by the first wave and was forced to shut down. And so they had already been applying the model then. So our goal was to extend this Wells-Riley model so that we could have a quick to run simulations, but to include the effects of the virus transport and the diffusion. And we did so by making the following modeling assumptions: that all the droplets are of the same size, carrying the same virus, that they are released with initial velocity of 0, that the droplets evaporate immediately to the equilibrium size, and that the turbulent mixing in the room causes the droplets to diffuse much faster than molecular diffusion. And this leads us to the governing equation of an advection-diffusion-reaction equation, where we have an advection by airflow term and also a term for the turbulent diffusion. On the right of the equation, we have a source for the infectious person and sinks for the ventilation, biological deactivation, and gravitational settling. We are modeling the infectious person as a continuous point source, and we are following the Wells-Riley model in modeling the ventilation, biological deactivation, and gravitational settling as first-order removal terms. As for the turbulent diffusion coefficient, we are following this result from Foot et al. 2020, which says that the turbulent diffusion coefficient K is proportional to lambda, which is the air exchange rate of the room, which is also a measure of the ventilation in the room, times a fraction of the volume, the room volume, to the number of air inlets to the power of 2/3. And we will be considering this for 4 ventilation scenarios: a very poor ventilation, a poor ventilation, and 2 ASHRAE recommended ventilations, in which ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. And before the pandemic, they had recommended a ventilation of about 3 air exchanges per hour. But after the pandemic hit and airborne transmission became a concern, they recommended a doubling of that to 6 air exchanges per hour. For the very poor and the poor ventilation scenarios, we are taking figures from a primary school, an air sampling of a primary school, which showed that these could be the sort of poor ventilations that our children are facing in schools. In our model, we are assuming this simplification of the airflow in the room. We are assuming that we have a rectangular room and there is no open window or doors. So all the ventilation is mechanical, and that is driven by an air conditioning on the left wall of the room. And the speed of the airflow is constant. And then the recirculation is driven by this loop that you see here. This allows us to perform a quasi 3D setup in which we are modeling 2 layers in the room. The first is the layer, the top blue layer shows the particles moving left to right in the room, driven by the air conditioning. And the bottom red layer shows the recirculation is the recirculating layer. And we follow this result by Van Hoof et al. And assume that the height difference between these 2 layers is about half of the room height. This leads us to a simplified ADR equation solved on the following domain. And because we are considering 2 layers, this essentially doubles the room length. And to model the recirculation of the air, we are assuming periodic boundary conditions. As for periodic boundary conditions for 2 of the walls. As for the other 2 walls, we are assuming 0 flux boundary conditions there. When we solve for the concentration in these 2 layers, we will then combine them by summing them together, and then dividing by the height difference between the 2 layers to obtain the total concentration at that point. And this problem has an analytical solution, which we obtain by considering the green function and the method of images. So this analytical solution allows us to implement this model quickly and to run quick simulations. Like to note that the concentration in the room is proportional to R, which is the droplet generation rate. The droplet generation rate for COVID-19 is currently unknown, but we have to make a few parameter estimates because of the novelty of the coronavirus that is affecting us all. So we are making the assumption currently that all particles, all droplets produced that become airborne currently carry the virus, and so we're following the droplet generation rate from Asadi et al. And we are assuming the efficiency of the mass from this result by Fisher et al. In which we are assuming that cloth masks have a constant efficiency of about 50%. And we also have to make the following assumptions about the biological deactivation rate and the gravitational settling rate, following in the results of Duramelin and Oliveira. And we apply our model to a case study of an average classroom of dimensions 8 meters by 8 meters by 3 meters, and in which there is one air conditioning unit producing an airflow of speed 0.15 meters per second. And we assume that the infectious person is in the middle of the room. And so we will have particular interest in points A and point B in this room, point A being 1 meter downwind from the person, which is the most dangerous location in the room if you keep a 1 meter social distancing away from the infectious person. And point B is in the corner of the room, literally the furthest place in the room that you can get away from that person. So our model will produce spatially dependent concentration results and resulting in these concentration contours. We decided to present the results for the poor ventilation and the ASHRAE recommended ventilation pre-pandemic because we believe these are the most likely scenarios that most buildings would fall into. So as we said before, the concentration can be scaled by R, the droplet generation rate, which is dependent on the activity of the infectious person. So you can see that right there in the contours as well. In the left plot for poor ventilation, you can see that the numbers are much higher for the concentration than in the good ventilation case on the right. But because ventilation the turbulent mixing is proportional to the ventilation in our model, there is a lot more spreading of the virus in the y direction in the plot on the right. So if we consider the concentration versus time plots for point A, which is downwind, 1 meter downwind from the infectious person, and point B, which is in the corner, we can see that in point A, just as we expected, the very poor ventilation and the poor ventilation are very much worse than the ASHRAE recommended ventilations. But in point B in the corner, you can see that initially the better ventilation scenarios have the concentration increasing faster. This is because, once again, the ventilation is proportional to the mixing of the air in the room. So the better ventilation scenarios have the concentration increasing more initially, but eventually the poor ventilation scenarios will catch up to and have a higher final concentration level. Using our concentration results, we can calculate the probability of airborne transmission. So we calculate the dose inhaled by this integral of the breathing rate times the total concentration at that point. We know that this is unchanged from the Wells-Riley model, with the exception that now our concentration result has a spatial dependence. And then we calculate the probability from a dose response model. In this case, K is the infectivity constant, which, as mentioned earlier, is still currently unknown for COVID-19. So we are using an estimate of 0.0069 from which we obtained from Voronin et al. 2020. But of course, this infectivity constant will be different for the different COVID variants that are out there. So we will have probability contours as the results of our model. So once again, we can see that the contour shapes are exactly the same as the concentration contours. But for the sake of making policy proposals, we also do use our model to calculate the time to probable infection, which is the time to obtaining 50% probability of infection or attaining the median infection dose. And so you can see here the time to probable infection for if an infectious person had been talking non-stop in that room, in a room of poor ventilation on the left, and for the ASHRAE recommended ventilation settings on the right. You can see the great difference that increasing the ventilation will have on the rate of the probability of infection. So if we examine the time to probable infection versus the air changes per hour at point A and point B, for point A down, which is 1 meter downwind, we can see that as the ventilation increases, we get more air changes per hour. The time to probable infection increases as we expected. But in point B in the corner, we can see that when we have very poor ventilation and we actually increase the ventilation a little bit, the risk of transmission actually goes, the time decreases to probable infection decreases, indicating that the risk is actually increasing, right? So that is because of the mixing. And so for very poor ventilation, the air is not as well mixed, so the risk actually in the corner is not as bad as in the poor ventilation case. But after that critical point, where near the poor ventilation scenario, then increasing the ventilation does increase the time to probable infection and lowers the risk of infection in the corner as well. So we have done a survey of the literature so that we can make comparisons of our modeling results. There isn't a lot of air sampling data, unfortunately, but we did find 3 air sampling data from hospitals, which we which our model produced good comparisons with. And we also compared it to a CFD simulation by Berner et al. Of the Guangzhou restaurant super spreader case, which also showed good agreement, and the expected number of infections in that case, the expected number of infections predicted by our model was close to the actual number of people infected in that super spreader case. Currently, we are working on extending the model to include non-uniform droplet sizes. So we are assuming that if we this modifies the ADR equation so that we are now looking for the concentration of droplets of a certain diameter psi. So you can see that changes are to make that as the droplet generation rate is now dependent on the droplet size, and also it affects gamma, which is the gravitational settling rate. So we intend to incorporate an after evaporation distribution from the BLO trimodal model by Johnson et al. 2011, which, as you can see, produces a lot of the small droplets which are very dangerous, especially when someone is reading or speaking. And then because our ADR equation is not changed a lot, the analytical solution still holds, and we can find the total concentration by integrating the concentration of the droplets over the diameter. Finally, we are also extending this work to include the effects of air purifiers. And so we intend to, for instance, we are studying this scenario where 2 people are seated across from each other on at a table, with an air purifier in between both of them. To summarize, we have developed an extension of the Wells-Riley type models that allows us to determine the space-dependent risk of infection, and this model can be applied to any location. Our model accounts for different ventilations, activities, mask wearing, the infectious dose, room size, the source location, and particle effects. It has an analytical solution which allows us to perform fast simulations. And our model can incorporate realistic droplet size distributions. And it will also be able to incorporate air purifiers in the future. Thank you.